Earth has an invisible force field. You can't see it, can't feel it, can't touch it. But it's the only reason you're alive. Right now, as you watch this, the sun is firing 1 billion tons of charged particles at Earth every second. Solar wind, traveling at 400 kilometers per second. Without our magnetic field, that wind would strip away our atmosphere. The oceans would evaporate into space. Earth would become a radiation-blasted wasteland, like Mars. Mars used to have a magnetic field, billions of years ago. Then it died, and Mars became a graveyard. Deep beneath your feet, 5,000 kilometers down, Earth's core churns, 2 layers. An inner core of solid iron, as hot as the sun's surface at 5,700 degrees Celsius, but kept solid by immense pressure. And surrounding it, the outer core, 2,300 kilometers thick, liquid iron and nickel. That liquid outer core isn't static, it convects. Hot iron rises from near the inner core, cools, sinks, rises again, like boiling water, but iron, at 4,000 degrees Celsius. And Earth rotates, once every 24 hours. That rotation, combined with convection, creates something called the Coriolis effect, deflecting the rising and falling currents into spiraling patterns. Liquid iron conducts electricity. Moving liquid iron creates electrical currents. Those currents generate a magnetic field. This is the geodynamo. That field doesn't stop at Earth's surface. It extends 60,000 kilometers into space, 10 times Earth's radius. We call it the Magnetosphere. And every second, it saves your life. The sun isn't just light and heat. It's also constantly ejecting matter. The solar corona, the sun's outer atmosphere, is so hot, over 1 million degrees, that hydrogen and helium atoms are ionized, electrons ripped away from nuclei. That ionized gas, plasma, escapes the sun's gravity. About 1 billion tons per second flows outward through the solar system. By the time it reaches Earth, 150 million kilometers away, it's traveling at 400 kilometers per second. That's 1.4 million kilometers per hour. It's made of charged particles, mostly protons and electrons, some helium nuclei, and because they're charged, they carry the sun's magnetic field with them. When that wind hits Earth's magnetosphere, 2 magnetic fields collide. Earth's field pushes back. Most of the solar wind is deflected, streaming around Earth like water around a rock. The magnetosphere creates a shock wave, the bow shock, 60,000 kilometers upstream from Earth. Behind it, in the magneto sheath, solar wind slows and heats up as it's forced around our planet. But some solar wind does get through. On the day side, where Earth's magnetic field lines meet the sun's field, they can reconnect, breaking and rejoining in new configurations. When that happens, solar wind particles are injected into the magnetosphere. Those injected particles don't reach the surface directly. They spiral along Earth's magnetic field lines. Those field lines converge at the magnetic poles near the Arctic and Antarctic. At altitudes of 100 to 400 kilometers, the particles collide with oxygen and nitrogen molecules in the atmosphere. Those collisions transfer energy. The molecules get excited. Electrons jump to higher energy states. When the electrons fall back to lower energy states, they release that energy as light. Green light. Oxygen at 100 to 200 kilometers altitude. Red light. Oxygen above 200 kilometers. Purple and blue, nitrogen. We call them auroras, northern lights, southern lights. They're beautiful, but they're also proof that right now, at this moment, Earth's magnetosphere is deflecting solar wind. Proof that some particles got through the shield, but were funneled harmlessly to the poles. May 2024. The most severe geomagnetic storm in 20 years hit Earth. Auroras were visible as far south as Mexico, as far north as the tropics. The magnetosphere was compressed by intense solar wind. Satellites experienced navigation errors. Some power grids saw voltage fluctuations. But the atmosphere stayed intact. Life continued, because the shield held. Venus is Earth's twin in size and mass, similar internal structure, likely similar iron core composition. So why doesn't Venus have a magnetic field? The answer: rotation. Venus rotates once every 243 Earth days. That's slower than its orbit around the Sun, 225 days. Earth rotates 243 times faster than Venus, and rotation is critical for the dynamo. Without fast rotation, convection in Venus's core doesn't get organized into the spiraling patterns that generate strong magnetic fields. Venus might have weak convection, weak currents, but no coherent dynamo. Result? No global magnetic field. Solar wind hits Venus directly, but Venus's atmosphere is so thick, 92 times Earth's surface pressure, that atmospheric loss is slow. The dense atmosphere creates its own weak magnetic barrier, the ionosphere, which provides some protection. Venus survives without a shield because it has too much atmosphere to strip quickly. Mercury is the smallest planet, barely bigger than our moon, but surprisingly, it has a magnetic field. Weak, only 1% of Earth's strength, but measurable. Why? Mercury's core makes up 85% of its radius. For comparison, Earth's core is 55%, Mars's is 50%. Mercury is essentially a giant iron ball with a thin rocky shell. That massive core still has a thin outer layer of liquid iron. Just enough convection happens, driven by cooling from above, to generate a weak dynamo. Mercury's magnetosphere extends only 1 to 2 Mercury radii. The solar wind compresses it heavily. Mercury orbits close to the Sun, where solar wind is 10 times more intense than at Earth. But weak is better than none. Mercury's thin atmosphere, almost a vacuum, means there's little to strip anyway. The weak field is enough. Mars once had everything. A thick atmosphere, maybe 1 bar similar to Earth's. Liquid water, rivers, lakes, perhaps an ocean covering the northern hemisphere. A climate warm enough for rain, and a magnetic field, generated by a dynamo in its molten core. That field shielded Mars from solar wind, protected its atmosphere, made the warm, wet climate possible. But Mars is small, half Earth's diameter, 1/10 Earth's mass. Small planets cool faster. They have higher surface area to volume ratios. Heat escapes. October 2024. Research from Harvard University refined the timeline. Mars's magnetic field lasted until about 3.9 billion years ago. Maybe even 3.7 billion years, later than previously thought. But eventually the core cooled enough that convection slowed. And something else happened. Research from the University of Tokyo in 2022 revealed the mechanism. Mars's core contains iron, sulfur, and hydrogen. As the core cooled, those elements separated by density. Iron sank. Sulfur and hydrogen formed lighter layers above. Once fully stratified, layered like salad dressing that settled, convection stopped. No convection, no dynamo, no magnetic field. The field weakened over hundreds of millions of years. By 3.5 billion years ago, it was gone. And then Mars died. Not immediately, gradually, over the next few 100 million years. Once Mars lost its global magnetic field, the solar wind attacked directly. Solar wind particles, mostly protons, slam into Mars's upper atmosphere at 400 kilometers per second. They collide with carbon dioxide, nitrogen, oxygen molecules. Those collisions transfer energy, enough energy to knock electrons off the atmospheric molecules. Ionization. Once ionized, once charged, those atmospheric particles become vulnerable. The solar wind's magnetic field exerts force on charged particles. It picks them up, accelerates them, drags them away from Mars. Some escape over the day side, where solar wind impact is strongest. Some escape through the polar regions, where there's no crustal magnetic field to resist. Some escape over the night side, in the magnetic tail where Mars's weak, induced magnetosphere is stretched by solar wind. NASA's MAVEN spacecraft, in orbit since 2014, has been measuring this loss. Current rate? Mars loses about 100 grams of atmosphere per second. That sounds small, but over billions of years? Catastrophic. But Mars isn't completely non-magnetic. When its global dynamo shut down, some magnetism remained, frozen into crustal rocks. Ancient lava flows, solidified when the field still existed, preserved magnetic signatures. These crustal fields are patchy, strongest in the southern highlands. Locally, they can be stronger than Earth's field, reaching 1,500 nanoteslas at surface level. You'd think these remnant fields would help protect the atmosphere. They don't. A 2020 study published in Journal of Geophysical Research found something counterintuitive. Mars's weak, patchy magnetic fields actually accelerate atmospheric loss. How? The weak fields can't resist the solar wind. Instead of deflecting it, the solar wind pushes the field lines backward, draping them over the night side of Mars. Those bent field lines create open pathways. Ions escape along those pathways 6 times faster than they would with no magnetic field at all. A weak shield is worse than no shield. Between 4 billion and 3.5 billion years ago, Mars lost most of its atmosphere. Pressure dropped from maybe 1 bar to 0.006 bar, current levels. With lower pressure, liquid water became unstable. Lakes evaporated, rivers dried. The ocean sublimated into space, or froze into subsurface ice. Surface temperature dropped. Mars became the cold, dry desert we see today. The evidence remains. Riverbeds that will never flow again. Shorelines with no ocean to lap against them. A planetary graveyard. All because the shield failed. 1969. Apollo 11. Buzz Aldrin collects a rock near the Eagle lander. Back on Earth, scientists measure its magnetic properties. Discovery. The rock is strongly magnetic. Magnetic field strength when it formed, 50 to 100 microteslas. But the Moon today has no global magnetic field. Just weak, patchy crustal fields, remnants frozen into rock. Over 6 Apollo missions, astronauts collected hundreds of rock samples. Many showed strong ancient magnetism, especially rocks from the far side, near the South Pole. For 50 years, scientists debated, did the Moon once have a dynamo generating a strong field? Or did something else create these magnetic signatures? May 2025. MIT researchers publish findings in Science Advances. Lead author, Isaac Narrett. They may have solved the mystery. The Moon did have a weak dynamo. Only about 1 microtesla, 50 times weaker than Earth's field today. Generated by a small amount of convection in its tiny molten core. But 3.9 billion years ago, a massive asteroid struck the Moon's near side. The impact that created the Imbrium Basin, 1,100 kilometers wide, one of the largest impact craters in the solar system. The collision vaporized thousands of cubic kilometers of surface rock. Temperatures exceeded 10,000 degrees Celsius. Rock turned to vapor. Vapor turned to plasma, ionized gas. That plasma cloud expanded rapidly. It couldn't escape the Moon's gravity completely, so it flowed around the surface, like a temporary atmosphere made of ionized rock. The plasma concentrated on the far side, directly opposite the impact point. There, for about 40 minutes, the plasma interacted with the Moon's weak magnetic field. Plasma is electrically conductive. The motion of ionized particles in the plasma created electrical currents. Those currents amplified the Moon's weak magnetic field, making it 10 to 100 times stronger, temporarily. Rocks on the far side were in the right place at the right time. They were hot from the impact's seismic energy, but cooling. As they cooled below their Curie temperature, about 580 degrees Celsius for iron minerals, magnetic domains locked in. They recorded the amplified field. After 40 minutes, the plasma dispersed. The field returned to its weak background state. But the rocks retained their magnetic signature. But there's more to the story. The impact didn't just create plasma, it sent shock waves through the Moon. Lunar earthquakes, moonquakes, converging on the far side. When an impact happens on one side of a sphere, seismic waves propagate through the interior. They converge at the antipodal point, directly opposite the impact. Rocks near the South Pole, on the far side, experienced intense seismic shaking. That shaking jittered the rocks, vibrating them, just as the magnetic field peaked. Normally, as rock cools, magnetic domains, tiny regions with aligned magnetic moments, form randomly. But if you shake the rock while it's cooling in a magnetic field, those domains align more strongly with the field. It's like tossing a deck of cards with tiny compass needles into the air during a magnetic storm. When they land, the needles all point in a new direction and stay that way. Impact plasma amplified the field. Seismic shaking helped the rocks record it. Together, they explain why lunar rocks show such strong ancient magnetism. If Earth's magnetosphere is a shield, Jupiter's is a fortress. Jupiter's magnetic field is 20,000 times stronger than Earth's. Its magnetosphere is enormous, extends 7 million kilometers toward the Sun. If you could see it from Earth, it would appear 5 times wider than the full moon in our sky. Inside that magnetosphere, radiation belts, trapped electrons, protons, and ions spiraling along magnetic field lines, accelerated to near light speed. Jupiter's radiation belts are 1,000 times more intense than Earth's Van Allen belts. They're lethal. NASA's Galileo spacecraft, which orbited Jupiter from 1995 to 2003, took cumulative radiation damage that degraded its instruments. Juno, currently in orbit, has its most sensitive electronics in a titanium vault, weighing 150 kilograms just to survive. And Jupiter's moon Europa? Surface radiation dose 5,400 millisieverts per day, a lethal dose for humans in hours. Why is Jupiter's field so powerful? Jupiter is massive. Its interior pressure is so extreme that hydrogen is compressed into metallic hydrogen, a state where hydrogen acts like a liquid metal, conducting electricity. That metallic hydrogen layer, thousands of kilometers thick, convects and rotates. The dynamo is unstoppable. Uranus rotates on its side, 98-degree axial tilt. Its poles point toward the Sun during solstices. Its magnetic field is equally bizarre. Unlike Earth, where the magnetic field aligns roughly with the rotation axis, Uranus's field is tilted 59 degrees from its rotation axis. And it's offset. The center of the magnetic field is displaced by 1/3 of Uranus's radius, not centered on the planet. As Uranus rotates every 17 hours, its magnetosphere wobbles wildly. The magnetic field points toward the Sun. 8 hours later, it points away. 8 hours after that, toward again. When Voyager 2 flew by Uranus in 1986, it detected intense radiation belts. But scientists couldn't explain where the energy came from. 2024 research solved the mystery. When Uranus's magnetic field points toward the Sun, solar wind compresses the magnetosphere dramatically. The field gets squashed. Magnetic field lines bunch together. That compression accelerates trapped particles, pumping energy into the radiation belts. When the field rotates away from the Sun, the magnetosphere expands. Particles escape. Uranus breathes, inhaling radiation every 17 hours, exhaling it, repeating forever. Chaotic, inefficient, but still a shield. Earth's magnetic field has weakened 9% over the past 200 years, and there's a region where it's weakening faster: the South Atlantic anomaly. Between South America and Southern Africa, the field is 30% weaker than average, and it's growing. Satellites passing through it experience higher radiation doses. Electronics glitch. Computers reboot. Data gets corrupted. The International Space Station's crew takes extra radiation exposure when passing over the region. Is this the beginning of the end? No. It's likely a precursor to something else. A magnetic reversal. Every few 100,000 years, Earth's magnetic field flips. North becomes south. South becomes north. We know this from the geologic record. Lava flows preserve magnetic history. Iron minerals align with Earth's field when they solidify. By studying rocks of different ages, we can map reversals. The last reversal? 780,000 years ago. Before that, 1.2 million years ago. The timing is irregular, unpredictable. During a reversal, the field doesn't disappear. It weakens, becomes chaotic. Multiple poles form temporarily, then reorganizes in the opposite orientation. The process takes 1,000 to 10,000 years, and life survives. The fossil record shows no mass extinctions correlated with reversals. The atmosphere stays intact. The ozone layer protects us from UV radiation. We'd experience more cosmic rays, more auroras at lower latitudes, but not catastrophe. Eventually, billions of years from now, Earth's core will cool, convection will stop, the dynamo will shut down. But by then, the Sun will have expanded into a red giant. Earth's surface will be scorched, maybe engulfed. The magnetic field will be irrelevant. For the next few billion years, we're safe. Our shield will hold. Magnetic fields determine habitability. Earth has one. Life thrives for 4 billion years. Mars had one, lost it, became a frozen desert. The Moon had brief, violent amplifications, not enough atmosphere to protect anyway. Venus never developed a strong field, but its thick atmosphere compensates. Mercury's weak field is barely enough, but enough. Out there, on exoplanets orbiting red dwarf stars, this matters even more. Red dwarfs produce powerful stellar winds, frequent intense flares. Without strong magnetic fields, rocky planets lose their atmospheres in millions of years, not billions. Magnetic fields are invisible, but they're the difference between oceans and deserts, between a living biosphere and a sterile rock, between Earth and Mars. But magnetic fields aren't the only existential threat. 66 million years ago, an asteroid 10 kilometers wide ended the age of dinosaurs. The Moon's face is a record of 4 billion years of bombardment. Earth's surface? Surprisingly smooth. Where are all the craters? We're in a cosmic shooting gallery, and we're overdue. This is Cosmic Canvas, where we reveal the invisible forces protecting worlds. Mars lost its shield, Earth kept one. That invisible difference made all the difference. Until next time, be grateful for things you can't see. Some of them are keeping you alive.